In this video, we discuss the convolution of two functions, then we state the convolution theorem, and then we apply the theorem in a couple of examples. So here's the definition of a convolution. If f and g are two functions of t, and they are defined for t greater than or equal to 0, then the convolution of f and g is also a function of t. And it can be written this way. The convolution of f with g is a function of t, and it's the integral from 0 to t of f of tau times g of t minus tau d tau. This is a special product, and we call it the convolution. Now, it turns out that it has this property. It has many properties, but it's commutative. The convolution of f with g is the same as the convolution of g with f. And that can be shown pretty easily just by doing a substitution. If I let u equal t minus tau, and I want to write everything over here entirely in terms of u, I can. Then this would be g of u in that case. Now, if I'm thinking of tau as my variable, and I am, when I make the substitution, I compute the derivative of u with respect to tau, so I get negative 1 times d tau. So negative du is equal to d tau. And so I can write everything up here entirely in terms of u and t. Well, in order to do that, I need to get tau in terms of u and t, so I will solve this equation for tau by subtracting t from both sides and then multiplying both sides by negative 1. That's just going to flip the order. So this is f of tau, which is now given by t minus u. And then we also need new limits of integration. So I've got this in terms of t and u, this in terms of u, or g and u, and this in terms of u. And then I need the bounds. But I don't want bounds for tau anymore. I want bounds for u. And in order to find those, we need to use the bounds for tau to find the new bounds for u. So the original upper bound was that tau, or was given by tau equals t. When tau equals t, u is equal to t minus t, so that's going to be 0. And then the original lower bound was given by tau equals 0. If we replace tau with 0 here, we're going to have t minus 0, which is t. So this becomes the convolution of f with g, which is a function of t. F of t minus u times g of u times negative 1 du, and our new bounds are 0 and t. Well, since I've got this negative 1 out front, I can flip those. It's just a property from calculus 1. And of course, multiplication is commutative, so we can change the order of that product. And we've got that. Now, isn't that the same as g of tau times f of t minus tau d tau, evaluated from 0 to t? It is. Using a u instead of a tau doesn't change anything. It's just a dummy variable. So we can go back to tau if we want to. And then we see that the convolution of f with g is the same as the convolution with g of g and f. So the order doesn't matter. So that's why this is often called a special product. It has a lot of the properties of multiplication. So that's the convolution. And here is the convolution theorem. If the Laplace transform of f and g exist for all s greater than a, and a has to be greater than or equal to 0. Then it turns out that the Laplace transform of the convolution, which is equal to the Laplace transform of this integral from 0 to infinity of f of tau times g of t minus tau d tau, is actually equal to this. It's kind of surprising. It's the Laplace transform of f times the Laplace transform of g, or f of s times g of s. Now remember how the Laplace transform itself is defined. This is the integral from 0 to infinity of e to the negative st times this integral times dt. And then you would evaluate that integral, that improper integral, with respect to t, and it turns out what you get is the product of the Laplace transform of f and the Laplace transform of g. And this can be used in a number of ways. Of course, you can use it forward and backwards. You have the forwards version of this. The Laplace transform of a convolution is just the product, and then you can use it backwards. The inverse transform of a product can be written as a convolution. If that integral that looks like this is pretty easy to evaluate, we can just evaluate that integral, and that would allow us to find the inverse transform of a product that looks like this. Now, in practice, we're going to tend to use it in the forward direction. I don't tend to use it in the backward direction. In the backward direction, I tend to use partial fraction decomposition more often than that, although it can be used as well, and we'll do at least one example like that. But we're going to use this convolution theorem typically in the forward direction in the context of what are called integral equations and integral differential equations. Those are like differential equations in that they contain an unknown function. But with a differential equation, you've got derivatives of an unknown function, and you're trying to figure out what that unknown function is. With an integral equation, you have integrals involving an unknown function. So you might have an integral that looks like this, and f of t might be the function that you're looking for, or g of t might be the function that you're looking for. If we can recognize that integral in our integral equation as a convolution, then we can take the Laplace transform of it, and then we can solve for f of s or g of s and try to find that function f of t by computing an inverse transform. And we can use it in the same way if we have what is called an integral differential equation, which just means you've got integrals involving unknown functions and derivatives involving the same unknown function in the same equation. But all of those can be handled now that we know the convolution theorem for taking the Laplace transform of a convolution. So let's apply this theorem. Let's apply it a couple of different ways. Let's apply it in the forward direction and backwards as well. So let's say that somebody wants you to compute the integral from 0 to t of tau times e to the tau minus t d tau. As soon as I see that integral, I'm thinking it's probably a convolution of two functions. Remember the pattern for convolution. This is the integral of f of tau or times g of t minus tau. So if I see a function of just tau, I'm going to think of that as my f. And the functions that involve t minus tau are going to be, or that the terms or factors that involve t minus tau, I'm going to think of that as my second function, g of t minus tau. So we've got f of tau equals tau, and g of t minus tau is e to the negative tau minus t. Well, I want to think of this as a convolution of two functions of t. Well, if f of tau is equal to tau, then f of t would just be equal to t. Now this one is a little trickier because I want to think of this as an input-output machine. My input is t minus tau. The output needs to have t minus taus in it in order for me to think about how the input is affected by this function. Well, I can make this right-hand side look like expressions that involve t minus tau if I factor out a -1 in that exponent. So e to the negative t minus, or tau minus t is -1 times t minus tau. -1 times t is negative t. -1 times negative tau is positive tau. And we've got that. So when I think that this is an input-output machine now, I'm saying g of some input is e to the negative of that input. So g of t must be e to the negative t. So this is the Laplace transform of the convolution of f of t, which is t, with g of t, which is e to the negative t. Well, according to our theorem, the Laplace transform of the convolution is the Laplace transform of the first factor times the Laplace transform of the second factor. If I saw this in an equation and I needed to compute the Laplace transform of it, I would probably use this method. So I'd say, oh, that's the convolution of these two functions. Take the Laplace transform of the first factor. That's t to the n. The Laplace transform of t to the n is n factorial over s to the n plus 1. If n is 1, that's 1 factorial, which is 1, over s to the 1 plus 1, which is s squared. And then this is the Laplace transform of e to the at, where a is -1. The Laplace transform of e to the at is 1 over s minus a. In our case, a is -1. So we're going to subtract -1, which is the same as adding 1. When we multiply those two guys together, we get this. So the Laplace transform of the convolution in this case is this. Now, the other option is if you have a convolution, you could actually work that out and find out what function of t that is, and then compute the Laplace transform of that function of t. My claim is that when you compute the Laplace transform of that function of t, you're going to get the same thing over here. It's probably going to look a little different. It's not going to have that common denominator like we have here. But if we got a common denominator, we could show that those are equivalent. So let's evaluate this and then show that the Laplace transform of the result of this integral is actually equal to this. And I also want you to see that this is actually a function of t. Even though it doesn't look like a function of t, it's a function of t. So let's compute it. I have the integral from 0 to t of tau times e to the tau minus t dt, or sorry, d tau. And I would use tabular integration by parts, where u is the polynomial and dv is everything else. Well, you want to compute the derivatives until you get 0. You're differentiating with respect to tau, because that's our variable here. You want to anti-differentiate with respect to tau as well. And then we would have this sign convention, plus, minus, so you multiply, and then you add and multiply, and then multiply by -1, and then you add. I'm going to factor out that e to the t minus tau in both cases, so we're going to end up with tau minus 1 times e to the t minus tau, evaluated from tau equals 0 to tau equals t. At tau equals t, we're going to get t minus 1 times e to the t minus t, which is e to the 0, which is 1, minus what we get when we plug in tau equals 0. So we're subtracting -1, so that's adding, times e to the tau minus t, where tau is 0. So it's going to be 0 minus t, which is -t. So that's that right there. And that means that the Laplace transform of this convolution is equal to the Laplace transform of this function of t, because that function of t is that value of the convolution. And that's going to be just using the linearity properties of the Laplace transformation, 1 over s squared minus 1 over s plus 1 over s plus 1. Now, if I got a common denominator, I claim I'm going to get the same result that I got using the convolution theorem. So the LCD in this case would be s squared times s plus 1. So I would multiply this guy by s plus 1 over s plus 1, and I would multiply this one by s times s plus 1 over s times s plus 1, and I would multiply this one by s squared over s squared. And if we get a common denominator, we'll see the denominator in this case is s squared times s plus 1. We end up with this, s plus 1, and then we have minus s times the quantity s plus 1. If we distribute the negative s, we'll have a negative s squared minus s there. And we have a positive s squared over there. S squared minus s squared is 0. S minus s is 0. So we end up with 1 over s squared times s plus 1. And you can see that that was much easier using the convolution theorem. I just recognized that as a convolution, and then I took the Laplace transform of each factor, and I got that, which is the same as the Laplace transform of this after you get a common denominator. Okay, so most of the time when you're using this, we're not using it in this way. Most of the time when I'm using this, I'm using the Laplace transform of a convolution in the context of solving an integral equation or an integral differential equation. So maybe you're solving an integral equation or an integral differential equation and you see something that looks like this. So you see the integral from 0 to t of f of tau times t minus tau cubed d tau. Maybe f of tau, or excuse me, f of t is the function that you're looking for that satisfies that integral equation. And this is just one term in your integral equation. Well, I would recognize this is the convolution of f of t and g of t, where f of tau is just equal to f of tau, of course, and g of t minus tau is t minus tau cubed. Well, this is taking the input and it's cubing it. So g of t will be t cubed. We're going to take a general input and we're going to cube it as well. So this is the Laplace transform of our unknown function f of t, which we're looking for, convoluted with the t cubed function. According to our convolution theorem, we get the Laplace transform of the first factor, which we'll call f of s, and we multiply by the Laplace transform of t cubed, which will be, if n is equal to 3, that's 3 factorial, which is 6 over s to the 3 plus 1, or s to the 4th. And I'd probably write that 6 in front of my f of s. Okay, so that's how we're going to tend to use it in this class. We're going to solve an integral equation, and the unknown function that we're looking for will be at least one of the factors of the integrand, if not the entire integrand. Now, some people also use this to compute inverse transforms of expressions that look like that. So you might say, what is the function? Or if I have an inverse transform of this, I'm trying to compute that. What I would typically do for something that looked like that is I would use partial fraction decomposition. Maybe you've got, let's do this, 2 over s times s squared plus 4. Well, I could use partial fraction decomposition for that. Or I could think of this as the product of 1 over s and 2 over s squared plus 4. Well, this is f of s, and this is g of s. Well, according to our theorem, the inverse Laplace transform of f of s times g of s is just the convolution of f with g. So this will be the convolution of f with g, where f is the inverse transform of f of s, which is 1 over s. The inverse transform of 1 over s is 1. And g is the inverse transform of 2 over s squared plus 4. This is s squared plus k squared. K squared equals 4. That means k equals 2. So I've got k over s squared plus k squared. Well, the inverse transform of that is sine of kt. So we have sine of 2t here. So the inverse transform of this can be written as the convolution of 1 with sine of 2t. Now, typically, I would replace t with tau in this function and replace t with t minus tau in this function and then evaluate the appropriate integral with respect to tau. To simplify our work, I'm just going to use the commutativity property of the convolution operator. And I'll just say that that's equal to that, which is defined to be the integral from 0 to t of sine of 2 times tau. And then we'd evaluate this function g of t equals 1 at t minus tau. Well, if you change the input of a constant function, the constant function stays exactly the same. So it's still going to be this times 1, and you're integrating with respect to tau. So we would antidifferentiate. The antiderivative of sine is negative cosine. Since I've got a constant multiplying my tau, I need to divide by that constant. I evaluate from tau equals 0 to tau equals t, and I subtract. So I have negative 1/2 of cosine of 2t, and then I'm subtracting a negative 1/2 times cosine of 0. Cosine of 0 is 1. So I end up with 1/2 minus 1/2 cosine of 2t. And actually, that can be written like this. You guys recognize that? That's a trig identity. I believe that's sine squared of t. But you could also use partial fractions for this, and you would end up in the same place. You would write this as a sum of a number of terms, and then you take the inverse transform of each of the terms, and you would get probably a result that looks like this. That's what I would recommend in this case, but if you prefer, you can say, hey, that's a product, and write that as a convolution, and then actually compute that convolution integral to find the original function of t. Again, though, for our purposes, we're going to tend to use the convolution theorem when we're solving integral equations. That's equations that contain integrals of unknown functions. And the work is going to look something like this, where the unknown function might be f of t or y of t or g of t, and that would be inside an integral with respect to tau evaluated from 0 to t. If we see that, then we know we can write that as a convolution, and we can actually solve for f of t by taking the Laplace transform of the entire equation, solving for f of s in this case, and then computing the inverse transform of f of s to get f of t back. And we're going to talk about that more in the next video. So just as a recap, what is a convolution? This is the definition of the convolution of f with g. This is a function of t. And this is defined for t greater than 0. And it turns out that the Laplace transform of a convolution is the product of the Laplace transforms. And that is kind of unusual, because this is the integral from 0 to infinity of e to the negative st times this integral times dt. Turns out that if you do some algebraic manipulation for all s greater than some value a, as long as f and g exist for all s greater than some value a, the Laplace transform of this integral is actually equal to the product of the Laplace transforms f and g. And we can use that backwards as well, although I usually don't. I just use this most of the time in order to solve integral equations.